So hey, Year 12, I thought I'd just pop a little recording together for the very last lesson on graph theory. And so you can watch this in advance of our lesson on Wednesday or at the start of our lesson, don't really mind. Okay, so let's just have a look here at some of the notes. So yesterday we looked at visiting all the edges, which is the Chinese postman problem. And that had a Eulerian flavour to it. Now we've got now we're looking at what's called the travelling salesman problem, where each of the vertices need to be visited. It's like door knocking, each vertex is a door, and so the salesman gets around each door. He wants to do that, or she, in such a way that we are hitting each vertex once, at least once, because we've got to knock on all the doors, but we want to do it in the most efficient way. It's the travelling salesman problem, and it has a Hamiltonian flavour to it because Hamiltonian cycles, remember, are concerned with visiting each of the vertices. But Hamiltonian cycles, do you remember, weren't as easy to find. There wasn't a certain way of knowing whether a graph was Hamiltonian. Although we were able to say that if each vertex had a degree greater than or equal to n over 2 for an n verticed graph, then it would be Hamiltonian. Okay, so, and since we're only going to be dealing with complete graphs in this piece of the course, this part of the course, and we're only going to be exploring the travelling salesman problem for complete graphs. We know there's a Hamiltonian cycle. In fact, there are going to be many, but the trick is to find the one that's the shortest. Now, that's the difficult thing. Now, all the writing here on the page is basically what I've just been saying. Now the upper bound, so there's an algorithm, but the algorithm doesn't take us to the exact solution. Disappointingly, the algorithm, and we have separate algorithms for an upper bound and a lower bound. So all we can do is find a range of lengths between which the ultimate length is, or the shortest length is. So to find the upper bound, this is our algorithm here. Pick a starting vertex, blah blah blah. We'll go through this with an example. So there's the upper bound is essentially a nearest neighbor algorithm, and we'll go through that in a sec. The lower bound is using a combination of Kruskal's algorithm. So I'm finding a minimum spanning tree. You remove a vertex. You're normally told which one to remove. It's a little bit of a faff, to be honest, but it gets us around each of the points, and we can find out if we can find a cycle between the lower and upper bound, then we know that it's we can find the minimum lies between the lower and the upper bound, but we don't know exactly the length. Okay, so let's have a look at this example and see if we can make sense of this. Okay, so we've got, so use the nearest, let's go through it, use the nearest neighbor algorithms starting at A. So we're starting at point A, and we're going to D first, right, A, to find an upper bound for the travelling salesman problem. So in order to find an upper bound, this is what we do, right? Let's go to the upper bound algorithm. Pick a starting vertex. Well, that's been picked for us. We're starting at A. Okay, so I'm going to get to work on this guy here. And so we're going to start at A, and we're going to go from A to D. All right, so that's going to be my first move. So I'm going to drop down from A to D. We've been told to do that, but we've only been told to do that, I think, because there's another path I could have taken that was also 2, because the first thing you do once you've pick a starting vertex, go to the nearest vertex not yet visited. So the nearest vertex is the one with the shortest edge. So from A, I could have gone to E4, D2, C5, B2. I could have gone to D or B. They said go to D first, so I did. Okay, from D, I now go to my neighbouring vertex of shortest length. So from D, I'm going to go to, I can either go to E, which is 5, C, which is 6, or B, which is 2. So obviously I'm going to go to B, which is 2, right? So I'm just going to head across to B like so, and I keep doing this until I have visited every vertex. Okay, so from B, I can't go to A, I've already visited A, I can't go to D, so I can go to E or C. Which is shortest, 6 or 3? Obviously 3 is, so I take it. Down I go. Now I'm at C. Now from C, I'm going to have to go to E because it's the only vertex I have not yet visited, and that has a length of 4, and so over I go to E. Okay, now I've visited all the vertices, so what do I do now? I go add one more edge to return to the starting vertex. Well, I've just got to go now. I know in a connected graph, I'm always going to be one edge away from the starting vertex, so I just join E to A, and that takes me, that's 4. And so now I add these up. The sum of these edges is an upper bound. All right, so there you are. So the upper bound, if I just sum those up, upper bound is equal to 2, 4, 7, 11, 15. Okay, so now I need a lower bound. So I'm going to remove all those highlighted strokes, and we're going to get to an upper bound. Now, sorry, a lower bound. Now, a lower bound, interestingly, you have to remove one vertex. Now, we are usually told, I've never seen a question where we're not told which one to remove. By removing vertex A, find a lower bound. Righto. So we're going to remove A. So A's out, and what we do, we also remove all the edges associated with A, right? All the edges that take A or connect A up with the rest of the graph. We remove all those. So it might be easier to redraw this graph, which I'm going to do just down here. So I'm going to redraw. So it'll just be E, B, D, C, right? So it'll be E, B. You won't necessarily need to do this once you get used to these questions, but just for this first example, just for clarity, I've removed A, so it's disappeared from my graph, so I don't really want to see it anymore. It's just cluttering up my scene. But all these edges are connected, all these vertices, are connected. And so there should be a degree of 3 on each because it's a 4 vertex thing now. Righto. So I've removed all those edges there and I've redrawn my graph. I'm looking for a lower bound now. Now, what do I do next? Well, I find the length of the minimum spanning tree for the remaining graph. So here's my graph. I now just want the minimum spanning tree. I need to put my lengths on here. My weights, EB is 6, BC is 3, DC is 6, and ED is 5. DB over here is 2, and EC is 4. All right, I'm just copying those down. Righto. So now I want my minimum spanning tree. Now, remember what a minimum spanning tree was? It was Kruskal's algorithm, and all we did was list in order, in ascending order, the lengths, right? So we go BC2, BC3, EC4, ED is 5, EB is 6, and so is DC. Okay, and then I go and select. Okay, so I'm going to take BC. I'm going to take BC. Hang on a second. What am I doing here? BCB. I've written that wrong. Sorry. Let's just backtrack out of there for a second. It's not, BC is not 2. BC is 3. BD is 2. So that should say BD 2. Righto. So I want BD first. That's down here. That's 2. So I take that, and BC 3. I always take the first 2. Now we need to be careful of cycles. I don't accept a cycle. So EC4, I can take that. That doesn't create a cycle. That's all good. So I've got 3 sides so far, and how many do I need in a 4 vertex? That's it. I'm done. I've got my 3. I've connected each of my vertices, and so I've constructed my tree. Right. So my tree has 9. Let's just make a note. That's not my minimum length, by the way. That's not my minimum. No, it's not my minimum. I'm just going to say that my minimum spanning tree is equal to 9. Okay, the last thing we do is we connect A, and we use the two. There are four, right? There are 1, 2, 3, 4 edges connecting A. We choose the two smallest to connect A, and we add that on to our minimum spanning tree. So what we end up with, we've got 3 sides there, and with these two we end up with 5 sides, which we have to have in a complete to visit all the vertices on a 5 pointed graph. I need 5 edges, so I need 2 more, and I'm going to choose the 2 connecting back to A that are my shortest. So I've got 2 2s there, so they're the ones I'll take, 2 plus 2. You see this is the last thing we have to do. Finally add the 2 shortest edges that reconnect the removed vertex. So I'm going to add 2 and 2 just here, plus 2 plus 2, they're my 2 shortest. 2 shortest, back to A. And I get 9 and 2 is 11 and 2 is 13. So my minimum is 13, my minimum bound, my lower bound. So therefore, lower bound equals 13. So I know my minimum, my shortest distance around and visiting each of my points lies no smaller than 13 and no larger than 15. So that's the best we can do. If we can find a Hamiltonian that gets me in that range, then I know that I've pretty much got the best I can get. So that's our sort of hybrid algorithm we use for the upper bound. We start on a vertex and we just bounce around, going the shortest distance each time to a vertex that's not yet been used until we've used them all. Then we take it back to the starting point. That's our upper bound, right? Our lower bound is we remove one vertex, we're normally told what it is, scrub out all the edges that connect it, then find the minimum spanning tree for the remaining graph and add the 2 shortest edges to reconnect the one you removed. That will give you a minimum, a lower bound. And if they're equal, then you've found your cycle. If they're equal. If you find a cycle that's equal to the lower bound, then you've found your minimum cycle. You've found you've solved the traveling salesman problem. If you can say if you can show that the lower and the upper bound are the same, or you can find a cycle that's equal to your lower bound, you've solved the traveling salesman problem. Otherwise, you just know that it lies in that range. Okay, so we can now do exercise 7E, and I'll give you a hand with that. See you soon.